Hey everyone, welcome to week 9 of the term. This week it's a bit of a different lesson, if I'm completely honest. So, the material this week will be based mostly on this. This will be what the discussion and the quiz are based on. However, I begin by delving into the first half of paleoclimate this week. And listen, this is entirely on you, but this is the most difficult material of the semester by far. So I'm breaking it up into parts 1 and 2 so that you can basically have 2 weeks at it. So this is on you if you choose to do it. If you don't, then you're going to have to do both parts next week. That's less pleasant. Just letting you know, being upfront. So I'm going to cover this today in this video. In addition to this is pretty straightforward stuff, as you'll get to see. So up to you. Fair warning, you really should get into this now so that next week there's less to get into. That's enough of warning. I will leave it up to you whether you choose to do that or not. So having said that, let's begin with the IPCC. As you can see, it's pretty short. The Intergovernmental Panel on Climate Change, IPCC, important. They are the ones that basically administer the work on climate change on a global basis, on a global scale. So having said that, let's see how the IPCC advises policymakers. In the end, those are the people at the government level, not just the United States, but really all states in the world, and how they react to it. So it was founded in 1988 when climate change was initially recognized as a global problem. It was envisioned by the UN Environmental Program and the World Meteorological Organization. They issue major reports roughly every 6 to 7 years. And we happen to be at one of those inflection points at the time of this recording, late 2021. So the role of the IPCC hasn't really changed. It's to assess in an objective, and remember the word objective means data-based, comprehensive, open, and transparent, the impacts on human and natural systems stemming from, look at that word again, anthropogenic, human-caused climate change worldwide. So that's their role. They themselves do not conduct any original work. They function as a collector. They are the ones that put together all kinds of meetings and gatherings, and then they collate all the work into big reports that are either assessments, special reports, and technical papers. So, but they themselves are not the ones doing the work. It could be a research consortium at a university, at a government-funded research facility. It could be a combination of many universities from the United States, like somebody at Stanford and somebody at Florida and somebody in Germany and somebody in Japan. And they get together and they conduct research, and they're the ones that put together the papers that then the IPCC will help combine into a big sort of umbrella type of work and discussion. The first one is the one that was actually updated in August 2021. As of the making of this video, this is not fully complete, but it is definitely more complete than the other two that follow. So the first working group, or working group 1, is the one that focuses on the actual hardcore science, the physical basis for climate change. And so they run computer models, they provide assessments about regional climates, and it's based on observational data collected at thousands of worldwide locations and ocean locations as well. This is the best image I could get of what the cover of it will look like. It's not the best, but you get a sense of what it will look like. Again, this is based on the old one, so I will forgo this one and get to this right here. So this is the AR6, it is called. This was AR5, so this is the old one. Notice 2013. So the 2021 AR6, by the numbers here, you get a sense of how many people, how many countries, what the process is. And notice 14,000 scientific publications were combined into this working group one report. So it's remarkably comprehensive. It is really an administrative juggernaut. It's a beast. So it takes a long time to do it properly. This is, for example, one of their slides that they provided, climate change at a glance. It gives you a sense of what's happening to CO2, sea level, Arctic sea ice, and glaciers across the Earth over the last X number of years. Here is how it tells you that the Earth is warming at an unprecedented rate, and whether you're looking at data from the revolution of the Industrial Revolution, 1800s through now, versus whether you're looking at it from the time of about 1,000 to 2,000 years ago by looking at ice data. So it gives you a sense of what's happening and how this little bar here, this little shaded area, is this area here. So that gives you a sense of, the dramatic increases that have taken place. And the fact that the influence of humans in the climate system is undeniable and unprecedented, quite frankly. So there's a video that's posted on Blackboard. It's working group one in their own words. This is still from AR5. There is no AR6 equivalent. However, there is a preview. And if you go to this website and you click on multimedia, it's about a 3-minute video. It has no words. It's mainly, it's a video, but it's just words on screen. No actual spoken word. Their update will come sometime either in late 2021 or in early 2022. We shall see. But anyway, I want to give you a sense of that. Now, working group 2, as the red shows you, the AR6 version is scheduled to be out February 2022. Regardless, working group 2 will consider the vulnerability and exposure of people. So it's the idea of adapting to climate change. That's what AR6 working group 2 will be, just like it is for AR5, quite frankly. But again, the issue here is vulnerability and adaptation to climate change. That's basically a roundup. There will be a new one for AR6 that will update this slide here. Regardless, lots of people, lots of comments, lots of interaction and cooperation between scientists from all over the world. Here's an example of some of their output. And this one, I hope they don't do away with it. It tells you how, there are possible futures: a good future, more green; a bad future, more red. So it's the idea of how resilient people are and what are some of the pathways that people, and by people I mean society, take. So the idea of being resilient means you can take a punch and come back. And along the way, there are decision points that you can make. And you can make a bad decision and another bad decision, and that leads to a bad outcome. Or you can make better decisions along the way, and that leads to good outcomes. I mean, you practice this in your daily life, so it's no different than financial decisions, or decisions about your health, or decisions about really anything in your life. And you can either have a good outcome or a bad outcome. Now, risk is something you cannot eliminate, but you can minimize it. And that's the whole idea here, okay? So it's assessing that risk and trying to come up with the best possible outcome even though you might still suffer some negative consequences. There's a video that's linked on Blackboard in their own words. It's still worth listening to because the main goal really won't change that much from AR6 to AR5 to AR6. Here's AR Working Group 3, which will be updated in March 2022. And Working Group 3 has been and will be about mitigating climate change. So what are the things you can do in order to either stop or reverse it? Meaning like doing away with using carbon sources for energy and all that kind of stuff. So assess the options for mitigating, making it better, doing away with the negatives and in placing more positive measures in order to have a better future outcome. The same basic idea here. And here they talk about, and again, this is a little bit dated. Notice the present line in this was 2010. We're at 2021 now. But this shows you, the idea of these are all fossil fuels, right? And the future is we want these colors to head in the down direction. So how do you do that? They have a video for it as well. These are some of the IPCC products, again, in 1990, 95, 2001, 7, 13, and the 6th assessment will be from 2021 into 2022. These are some of the special reports. Special reports are used to provide an assessment about a specific issue. Again, you see them there dating back all the way to 1997 and as recent as 2020. So these are like one-time good deals kind of thing. Think of it as like a big research paper rather than one of these AR working group reports, which are pretty standard and they change little over the years. These are individual, specific, special reports. Again, about a specific issue like land use, renewable energy, carbon dioxide capture and storage. Again, all these things are always being looked at. And that is the first presentation. Again, pretty straightforward, quite frankly. Definitely worth understanding. Even though it's easy, it doesn't mean it's not important. You should definitely know what the IPCC is, what they stand for, what they are hoping to accomplish with all these reports, okay? So having said that, now I want to move on to paleoclimate. And paleoclimate is important because this is how scientists reconstruct climate from the distant past. Okay, so paleoclimate is a study of the past or ancient climates by using what are called proxies. And a proxy is nothing more than an approximation, meaning you didn't have weather stations 1,000 years ago, 10,000 years ago, 500,000 years ago. So if you didn't, how do you reconstruct the climate? How can you tell that it's warmer now than it was, say, 400 years ago? How do you do that? And so there is no natural, the thesis here is that there's no natural process that is responsible for the warming that we're seeing today. Okay, so the increase in heat trapping gases, we talked about that in the greenhouse gas presentation, leads to what we now call climate change. So given the Earth's past history, climate change is the rule, not the exception. We've been warmer, we've been colder. So the reality is Earth changes quite a bit in geologic time. Unfortunately, humanity has only been around really for about 11,700 years as far as civilized human groupings. So therefore, we only know the Earth as it is now, roughly. Okay. So from about 2 million years ago until about 11,700 years, the Earth was in a cold period. Roughly that 11,700 year figure is when the Ice Age is believed to have roughly ended. And then we sort of enter the era that we're in now. So where do humans fit into this equation? So here's an image from the textbook. It's a great image. You have to first look at it on the x-axis. You have time. So 0 is now. 2 is 2,000 years ago, 10,000 years ago, 500,000 years ago, 5 million years ago. Get it? So this figure shows you how temperature has roughly evolved over time. All the ice in the world can tell you about here. From here on out, you have to look at the rock record, and that's not something we're going to do in this class. So now, let's look at the idea of tracing climate back a long, long time ago. So we're talking about plate tectonics, continents shifting, volcanoes, the growth of mountain chains, meteorites, and the release of methane that may have been frozen. All of these can change climate without any human intervention. Okay? Now, these are all affected, of course, by both positive and negative feedbacks. And remember, a positive feedback is counteracting, and a negative feedback is, a positive feedback is reinforcing, my bad. Positive feedback is reinforcing, a negative feedback is counteracting. My apologies there. So if the global temperature is warmer today than for most of the Earth history, about 50 million years ago, there was a gradual cooling as the Himalayan mountains began to form. That is when basically what we know today as India collided with Eurasia and formed that crumple zone that we call the Himalayan mountains today. This drew down carbon as rocks began to form through chemical reactions within the atmosphere, and the Earth cooled. And you can actually see that right there. This is when the Himalayan mountains formed. Now, let's keep going. The last 2 million years, we've had glacials. That's an ice age. And we've had interglacials. And the word inter means in between. So in between glacials, you have warm periods. And so basically that era is called the Pleistocene. And that is from roughly about 2.6 million years ago to about 11,700 years ago. That generally is accepted as roughly the end of the last ice age. So, think about the idea of when the last ice age formed, New York State was covered in ice. It started to warm rapidly after about that 11,700 year point, and numerous glacial forms began to form, like Long Island, for example, like the Catskills and the Adirondacks. And if you think about New York State, like the Finger Lakes region, these are all glacial landforms that formed as the glaciers retreated away from that area. So now, we're currently in what's called the Holocene. Some people call it the Anthropocene. Get it? Anthro, human. Regardless, that is roughly the period 11,700 years ago to now. It has been roughly stable, and it has coincided with the growth of human civilization. So notice this line, and this is what I want you to focus on. Notice how during most of human civilization, the Inca, the Maya, the ancient Egyptians, the Chinese dynasties. Notice how relatively flat the temperature line has been. So what I want you to get out of this is human civilization has coincided with a period when temperature has been roughly stable. And when temperature is stable, agriculture can happen, civilization can happen, human groups can grow. Before that, the temperatures change a lot. Cold, warm, cold, warm. And it is much more difficult for humanity to get going. So, do you follow that? I mean, even within this relatively stable region, there was a little bit of an ice age back in the 1500s to about the 1800s, but it was very short-lived and not as cold as other places. So that's the idea there. Now, we study past climates by looking at things like proxies. And the word proxy is just nothing short, it's only a short thing for approximation. Proxies will serve as a record of the changing climates and is a distinct chemical telltale sign. Okay, so let's look at what are some of the possible ones. Ice is the most common. Soil, tree rings. The tree ring can only tell you so much. Coral, and fossilized plankton that are called foraminifera. And this is pretty important. Foraminifera. And so this and ice cores yield the most, or the deepest or longest possible ice temperature approximations that you can possibly get anywhere. So these are what some of the cores look like. It's literally a tube of ice that's been extracted from a glacier, either in Antarctica or Greenland. Okay, there's been a direct effort by many countries, universities, and research facilities to collect as much of this as possible. Again, foraminifera, they are basically made up of calcium carbonate shells. And calcium carbonate, notice, has calcium in it, but it also has oxygen, and this becomes important. So this expedition called JOIDIS, Joint Oceanographic Institutions for Deep Earth Sampling, notice it has a drill in the middle of the ship. Looks very awkward, but it's important because they go into the ocean and they sample the ocean floor. In this case. So deep sediments cores are extracted and they are cataloged and photographed. And you can extract what some of the little bits of little seashells, basically what they look like. And these seashells are easy for me to say, right? These seashells are made up of calcium carbonate. These are ancient ones. And so these deep sea sediments, these are one-celled organisms, and they form the base of the food chain in the oceans. They die, and their shells settle into the ocean floor, and they become part of the sediment layer. Shells, again, are made up of CaCO3, calcium carbonate. Water is H2O. Notice how they both have O in them. So this is the key right here. So now let's look at, this is where it becomes a little bit more interesting. Oxygen comes in 3 flavors, 3 isotopes. Each isotope has a different number of neutrons, and hence the mass number is different. So light oxygen, 16, is lighter than 17, which is lighter than 18. So a molecule made up of H216O is lighter water than H218O. That's called heavier water. So light water, as you might imagine, evaporates more easily. Heavier water falls out as rain or snow sooner because it's heavier. Get it? So now, in the tropics, you have more evaporation, and you have more evaporation because it is hotter. So because it is hotter, there is more H218O left behind because it's heavier. Get it? So the water vapor that makes it further north is richer in 16 oxygen because it's lighter. Get it? It remains there in the atmosphere longer. As a result, water vapor that is rich in 16 moves further towards higher latitude, and most of the H218O is left behind. Now, so water vapor near the poles at high latitudes is depleted in 18, and it is enriched in 16. Remember, water vapor is still H2O. It's just in vapor form. So now here's from the book. I know this is both a good and a crappy image. So let me try to situate you. This right here is the state of Florida. I know it's hard to tell. This is North Carolina. This is Long Island. This is New England. This is Canada. This is Greenland. This is Puerto Rico and Cuba and the Caribbean. Okay? So I know it's a weird angle that they gave you that, but let's look at, this is the tropical area, right? It's hot. So there's more evaporation. So the heavy 18 condenses and falls off. So near the poles, way up here by Greenland and northern Canada, water vapor is depleted in 18 because it fell here. So here it is rich in 16. Make sense? So now you're separating at this point. What's happening is nature is separating heavier water from the lighter type. So now ice cores then record changes in temperature. So measure oxygen isotopes in the ice cores, and in the colder regions, there is less 18O in the ice because it rained out. So as a result, if you're going to do a ratio in the ice, there's little 18, more 16. And then in warmer times, there is more 18, less 16. And we'll get into the reason for that now. So high latitude water is enriched in 16. Remember, it's lighter. It can make it further north more easily. During a cold period, a glacial period, that 16O is tied up in the ice. Therefore, the seawater is richer in 18. Why? Because the 16 is in the form of ice. And during a warm period, as the ice melts, that 16O, which was tied in the ice, melts and it's released into the ocean. So the water then becomes richer in 16. So the little animals, the forams or foraminifera, their calcium carbonate, which has O in it, the oxygen in their shells is representative of whatever O there is more of in the water. So now, oxygen in the CaCO3 will match the composition in the seawater. So during a period of cold or a glacial period, you're going to have this ratio, a high 18 to 16, because the 16 is tied up in the ice, and during a warm period, it's going to be lower because more of the 16 is going to be in the water. And this image here Dr. Applebaum did this. I love it. It's a great, great image. Imagine sea level. This is the ocean floor, and this is a big chunk of ice on land. During a cold period, all the 16, well, maybe not all of it, but most of it is going to be tied up in ice. So the water is going to be high in 18, low in 16. So the little shells are going to be richer in 18 because there's more of it. Now, go to a warm period. Notice the little big chunk of ice turned into a little nub of ice. All that 16 is now in the water. So now the ratio is going to be smaller 18, greater 16. So the little seashells are going to represent that or show that. So that's how you sort of begin to sort of look at, these little chemical telltales tell you whether, shells from a long, long, long time ago would have lived in warm water or cold water. And if they lived in warm water, it was a warm period. If they live in a period where there was where this was the issue, where there was more of this in the water, therefore there was more of this in the seashells, that tells you it was a cold period. So it's like a little bit of an investigative report. Some of the patterns as far as glacial, so ice cores, cooler temperatures, deep sea cores as well. There is the idea of an interglacial. This is a warm period. Okay, cold period, warm period. Roughly, there have been major glacials and interglacials roughly every 100,000 years, roughly. Stadials are called minor cooling, so that would have been the little ice age that happened in Europe, say back in the 15, 16, and 1700s. And interstadials would be minor warmings. The Eemian, this is a period that lasted roughly about 125,000 years ago, is a period that is roughly like Earth is now. So it's of interest to scientists. Of course, the difference being humans were not a part of it then. And here's what the ice sheet would have looked like. It's called the Laurentide ice sheet. It covered basically all of Canada, most of Alaska, and a good chunk of the northern United States. Now, this didn't all form at once, but this is roughly what would have been covered by ice. So as you can see, New York State is a completely glaciated, formed landscape. Following the last interglacial, again, we're talking about the idea of, when did the last glacial happen and the last interglacial? Well, we're roughly in it now. And so over the past 500,000 years, there have been several cycles, 5 ice ages, periods of break, where some areas have been colder, warmer. Really, climate it's hard for humans to sort of grasp the time scales because we tend to live very, very, very short lives compared to geologic time. But as you can see, it's been a constant ebb and flow of cold periods and warm periods. The only difference is now we have 7.6 billion humans on Earth and civilization and technology and cities. And so we're more in peril because of how our civilization has taken over the planet. And we're so dependent on now technology and all that. Again, post-glacial conditions, temperatures on the rise within a few thousand years of the last end of the ice age. The last ice age peaked about 20,000 years ago and then began to retreat. The only remnants that remain would be Greenland and Antarctica. So that is the end of the presentation. Let me take you back to, getting you to think about this part of the presentation, even though it gets into it next week. At least begin to look into it now this week. The IPCC stuff is actually pretty straightforward. So give that its due attention, but don't leave this until week 10. Get to it this week, and you will thank yourself later. In any event, I hope you're doing well. If you have any questions, let me know. And I look forward to dealing with you sometime in the near future. Talk to you soon. Bye.